This should not be possible. I want you to pause for a second and really think about the ground beneath your feet. Beneath you is a planet. A sphere of molten iron, rock, and water that weighs 6 trillion kilograms. That number is so large it's a joke, 6 followed by 24 zeros. Its gravitational pull is so immense it holds our oceans down, sculpts mountains, and casually lassos the moon into a permanent, silent dance. This force governs everything you know about weight, falling, and being tired at the end of the day. Now go to your kitchen. Take a tiny, cheap magnet off your fridge. The kind that holds up a takeout menu. Now hold it over a paperclip. Click. You just defeated a planet. That little magnet, weighing a few grams, has just overpowered the collective gravitational pull of 6 trillion kilograms of rock and iron. Effortlessly. Without breaking a sweat. This isn't just a party trick. This is a cosmic crime scene. This is a glitch in the matrix. A fundamental contradiction sitting right there on your kitchen counter. It's the universe screaming that one of its most foundational rules is not what it seems. Is gravity secretly a pathetic weakling, or is it the most powerful force in the cosmos, just hiding its true strength? Tonight, we're not just asking a question. We are putting reality on trial. This is the science audit. Alright, every good investigation starts with a lineup of the suspects. In our universe, the rulebook for how anything happens is written by just 4 fundamental forces. They are the puppet masters, and everything else is just a show. First up, the flashy one you just saw in action, electromagnetism. Think of this force like a global social network. It runs on 2 types of charge, positive and negative. And just like on social media, opposites attract and like charges repel. This force is a drama king. It's incredibly strong, loud, and responsible for almost everything you experience in your daily life. It's the force creating the light hitting your eyes right now. It's the force that binds atoms together into molecules, making your desk solid instead of a pile of dust. It is the architect of chemistry, biology, and all of technology. But here's its crucial weakness: it can be completely neutralized. For every positive charge in an atom, there's a negative electron nearby. In almost every large object you see, a tree, your dog, this entire planet, the positives and negatives are perfectly balanced. The force is still raging at the atomic level, a chaotic storm of attraction and repulsion, but from a distance, it all cancels out into a quiet hum of neutrality. Your fridge magnet works because it's an exception. Its atoms are all aligned to point their magnetic fields in the same direction, creating a focused, coordinated army that breaks the neutrality and unleashes its true, staggering power. Next, we have to zoom way in, deep inside the heart of an atom, to meet the strongest suspect of all, the strong nuclear force. This one isn't a social network, it's a family argument locked in the basement, and it's not letting anyone out. Its power is almost indescribable. Its one and only job is to bind tiny particles called quarks together to form the protons and neutrons in an atomic nucleus. And it has to be this strong to overcome the immense electromagnetic repulsion of all those positively charged protons crammed into a tiny space. Without the strong force, every atom in the universe, heavier than hydrogen, would instantly disintegrate in a flash of electromagnetic rage. But here's the catch: the strong force has an incredibly short leash. Its power drops to virtually zero if you go much beyond the diameter of a single proton. It is the ultimate bouncer. Its authority is absolute, but only within the microscopic confines of the atomic nucleus. To us, out here in the big world, it's completely invisible. Then there's the oddball, the ghost in the machine, the weak nuclear force. This one is the secret agent of the cosmos. It's subtle, strange, and it specializes in identity theft. The weak force is what allows a particle to change its fundamental nature. It can turn a neutron into a proton, or vice versa. This might sound obscure, but it's the engine of the stars. In the core of our sun, the weak force is what allows hydrogen nuclei to transform and fuse into helium, releasing the energy that powers our entire planet. It's the universe's quiet alchemist, turning lead into gold, or more accurately, protons into neutrons, enabling the chain of radioactive decay that makes the universe interesting. It's weirder than the others, violating symmetries they respect, and acting over even shorter distances than the strong force. A true enigma. And that brings us back to our victim, or is it our prime suspect? Gravity. The outlier. Those first 3 forces, they all operate in a similar way. They are what physicists call quantum fields. The easiest way to picture this is to imagine that all of space is filled with invisible, intangible oceans. There's an electromagnetic ocean, a strong force ocean, a weak force ocean. particles like electrons and quarks are like localized vibrations or ripples that travel through these oceans. Their interactions are like waves crashing into each other. Gravity doesn't play that game. Gravity is different. It's special. According to Einstein's theory of general relativity, gravity isn't a force or an ocean at all. Gravity is the shape of space and time itself. It's the geometry of the stage. Massive objects like the Earth don't create a pull. Instead, they bend and warp the very fabric of space-time around them, like a heavy bowling ball placed on a stretched-out rubber sheet. And smaller objects, like us, the moon, or a falling apple, are not being pulled. We are simply following the straightest possible path through that curved, warped space-time. We are all cosmic sledders, sliding down the geometric slopes carved by matter and energy. And here's the crucial difference. Unlike electromagnetism's pluses and minuses, gravity only has one flavor. It always attracts. There's no such thing as negative mass or anti-gravity. So while the other forces are busy canceling each other out, every single atom in the universe adds its tiny, infinitesimal warp to the geometry of space-time. It always adds up. This makes the magnet paradox even worse. The force that is cumulative, inescapable, and literally shapes the fabric of the cosmos, gets punked by a kitchen gadget. How? To even begin to answer that, we have to look at the numbers. And this is where the mystery becomes a full-blown crisis. In physics, the raw strength of a force is quantified by something called a coupling constant. It's essentially the volume knob for that force, telling us how strongly particles respond to it. If we put the volume knobs for electromagnetism and gravity side by side, the comparison is absurd. Electromagnetism is roughly 10 to the power of 36 times stronger than gravity. Let's be clear, that number, a 1 followed by 36 zeros, is so colossally large that it's just a string of symbols. Our brains didn't evolve to grasp it. So let's build a ladder of analogies. Imagine the force of electromagnetism between two protons is the entire wealth of Jeff Bezos. On that same scale, the force of gravity between them would be less than a single penny. Not enough to even notice. Let's try again. If the strength of electromagnetism were the height of the Empire State Building, the strength of gravity wouldn't even be the thickness of a sheet of paper. It would be 100 billionth the size of a single proton. It is, for all intents and purposes, zero. So let me restate the question that drives everything we do in physics. How is it that we even feel gravity at all? And the answer, as we said, is patience and teamwork. While electromagnetism's titanic strength is neutered by cancellation, gravity's almost non-existent whisper, added up over every single atom in the planet, slowly, inexorably, becomes a roar. It's the ultimate victory of quantity over quality. But this vast difference in strength isn't the real crime scene. It's a clue. The actual mystery, the thing that keeps thousands of theoretical physicists awake at night, staring at their ceilings, is something called the hierarchy problem. And it all centers on one famous, and famously misunderstood, particle, the Higgs boson. We can't go on without truly understanding the Higgs. It's often called the God particle, which is a terrible name. A better one is the status quo particle. The Higgs field, which permeates all of space, is what gives fundamental particles their mass. But it doesn't do it by gifting it to them. It's about interaction. Picture that cosmic molasses again. Some particles, like the photon, are like perfectly polished needles. They slice through the Higgs field without interacting at all. So, they have zero mass. Other particles, like the massive top quark, are like big, sticky, awkwardly shaped spoons. They get bogged down, constantly interacting with the field. That resistance to being pushed around, that inertia, is what we measure as mass. So the Higgs field is fundamentally important. And the measured mass of the Higgs boson particle itself, a vibration in that field, is about 125 gigaelectronvolts, or GeV. This number effectively sets the energy scale for our everyday world. It's known as the electroweak scale, around 246 GeV. Think of this as our comfortable home in the valley. It's the energy at which particles have the masses we know and love, where atoms are stable, and chemistry works. But physics tells us there is another scale. A final scale. A true, fundamental summit of reality. It's the energy where gravity is no longer a whisper, but becomes just as strong as all the other forces. Where our ideas of smooth space-time completely break down into a chaotic, probabilistic foam. This is the Planck scale. And it sits at an energy of about 10 quintillion GeV. That's a 10 with 18 zeros after it. So, our home in the valley is at 246. The summit of reality is at 10 quintillion. That's a gap of about 16 orders of magnitude. 16 zeros. Once again, This number defies human intuition. So let's try. If the electroweak scale, our world, was the thickness of a single human hair, the Planck scale wouldn't be the top of a mountain. It would be the edge of the observable universe. If our scale was a single second, the Planck scale would be 100 times the current age of the universe. The gap is not large. It is the definition of cosmic absurdity. Okay, so there's a big gap. So what? Here is the problem. In quantum mechanics, nothing is ever alone. The vacuum of space is not empty, it's a roiling, bubbling, chaotic sea of virtual particles that flicker in and out of existence for impossibly short moments. This quantum foam is not a metaphor, it's a measurable reality. And these virtual particles have a profound effect. When the Higgs boson travels through space-time, it is constantly interacting with this storm of virtual particles. And these interactions, which we call quantum corrections, should add energy to the Higgs. They should change its mass. And here's the killer point. The size of that change should be proportional to the highest energy scale available in the theory. That's the Planck scale. Let's try an analogy. Imagine the Higgs boson is a tiny wooden boat. And the quantum corrections are the waves on the ocean. Our theory of quantum mechanics doesn't just predict a gentle swell. It predicts a permanent, raging, cosmic hurricane, with waves quintillions of feet high. The Higgs boat should be instantly, violently, picked up and slammed against the top of the highest wave. Its mass should be dragged all the way up to the Planck scale. It wants to be heavy. Every natural calculation we can do screams this from the rooftops. And yet, when we go to the Large Hadron Collider and measure the Higgs, there it is. Floating serenely at 125 GeV. Our boat isn't at the crest of the hurricane. It's floating in a perfectly calm, meter-wide patch of water right next to the shore, as if the storm doesn't exist. For this to happen, the bare mass of the Higgs, a starting value in our equations, and the sum total of all the fury from the quantum storm have to cancel each other out with a precision of roughly 1 part in a quadrillion. 1 part in 10 to the 16. It means the storm's fury and the boat's initial condition are tuned to cancel each other out to the 15th decimal place. This is not like balancing a pencil on its tip. This is like machining 2 continent-sized pieces of metal to be so perfectly flat that when you put them together, there isn't a single atom's width of gap between them anywhere. This isn't natural. Physicists have a word for it, fine-tuning. And it's the biggest smoking gun in all of fundamental science. It tells us we are missing something profound. So, let's audit the conspiracies, the theories that try to explain this impossible calm in the middle of the storm. First up, and maybe the most famous solution, Hypothesis A, gravity isn't weak, it's just diluted. This is the radical theory of extra dimensions. Let's refine our analogy. Imagine you have a bright laser pointer. If you shine that beam across a room, it stays focused, intense, and bright. Now, imagine you take that same energy from the laser and put it into a bare light bulb. The bulb illuminates the whole room, but at any given point, the light is much fainter, much weaker. The energy didn't disappear, it just spread out in all directions. The theory of extra dimensions proposes that this is exactly what's happening to gravity. The idea is that our three-dimensional universe is just a sheet, physicists call it a brain, floating in a higher dimensional space called the bulk. The other 3 forces, our laser pointers, are stuck to this sheet. They can only travel along our 3D world. But gravity, being the geometry of spacetime itself, is the light bulb. It is free to radiate its influence out into these extra spatial dimensions that we cannot see or access. So gravity's true intrinsic strength, up close at the fundamental Planck scale, is exactly as powerful as the other forces. But its influence spreads out across all these extra directions, and by the time its effect reaches us back on our little 3D brain, it feels incredibly faint. Just like the light from the bulb across the room. The hierarchy isn't a problem of different strengths, it's a problem of different geometries. This isn't just a cool story. It makes concrete, testable predictions. If these extra dimensions are large enough, we should see tiny, minuscule deviations from Newton's famous inverse square law of gravity, but only at very, very small distances, sub-millimeter scales. Imagine 2 objects get incredibly close. Some of gravity's force lines that were leaking into the other dimensions would now be able to go directly between them, and the force would appear stronger than it should. In labs around the world, scientists are conducting these tabletop experiments. They use things like tiny vibrating plates and exquisitely sensitive torsion balances, shielded from all seismic noise and electromagnetic interference, trying to measure gravity at 40 or 50 microns. It's an attempt to literally poke another dimension. So far, Newton's law holds firm. But every new experiment that pushes the boundaries smaller tightens the noose on these theories. Another test is at the LHC. If we smash particles together with enough energy, we might create a graviton, a particle of gravity, that gets kicked off our brain and vanishes into the bulk. It would look like energy has disappeared from our experiment, a huge red flag. No such signatures have been found. Yet. Okay, so if gravity isn't leaking, maybe something is actively shielding the Higgs from the storm? Hypothesis B: protective symmetries. The leading contender for decades was a beautiful, elegant, and powerfully compelling idea called supersymmetry, or SUSY for short. It proposes a deep, hidden symmetry at the heart of reality. The idea is that for every known particle, there is an undiscovered, heavier superpartner. For every quark, there's a squark. For every electron, a selectron. A shadow particle for every particle in our world. So how does this magic shield work? Remember the quantum storm? It turns out that in quantum math, the contributions to the storm from the two basic types of particles, fermions, like electrons, and bosons, like photons, have the opposite sign. They naturally push in opposite directions. The problem is, in our standard model, they don't balance. But supersymmetry says that for every fermion, there is a partner boson, and for every boson, a partner fermion. When you add up the storm waves from a particle and its superpartner, their contributions to the Higgs mass cancel out. Perfectly. Mathematically. Beautifully. It's like having two identical but opposite sound waves. When they meet, they pass through each other in perfect silence. Supersymmetry provides a natural, automatic cancellation. The pencil isn't balanced by luck, it's held perfectly stable by a second, invisible, upside-down pencil. For decades, this was the great hope of theoretical physics. It was too elegant not to be true. But this raises the most obvious and now painful question: if this shadow world of superpartners exists, where is IT? The Large Hadron Collider was expected to be a superpartner factory. Physicists were placing bets on which one would be discovered first. And then years passed. They cranked up the energy. They collected mountains of data. And they found nothing. Not a single trace of a squark, a selectron, or anything else. This has caused a crisis of faith in the physics community. It doesn't kill the theory, the partners could just be much heavier than we thought, hiding at energies beyond the LHC's reach. But that requires its own fine-tuning, undermining the original point of the theory. The beautiful protector has failed to show up. Which brings us to our final, most philosophically jarring hypothesis. The one that makes physicists squirm. Hypothesis C: selection effects. What if there is no mechanism? No extra dimensions, no secret symmetries. What if the answer is simply, we got lucky? This is the controversial but powerful idea of the multiverse. Imagine an eternal, cosmic process that is constantly budding off new universes, like bubbles in a foam. And in each bubble, the fundamental constants of nature, the speed of light, the strength of forces, and yes, the mass of the Higgs boson, are set randomly. In the vast, vast majority of those bubble universes, the laws of physics are followed naturally. The Higgs mass gets dragged up to the Planck scale. In those universes, nuclear forces work differently. Stable atoms are impossible. Stars either don't form or burn out in a microsecond. They are sterile, dark, and dead universes. But in a vanishingly tiny fraction of those bubbles, 1 in a quadrillion, perhaps, by sheer, dumb, random luck, the numbers happen to fall just right. The bare mass and the quantum corrections happen to cancel. A universe is born with a light Higgs. A universe where atoms can be stable. Where stars can burn for billions of years. Where planets can form. Where complex chemistry can emerge, and where, eventually, on one small blue world, intelligent beings evolve who are capable of building instruments and looking up at the sky and asking the question, wow, isn't it an amazing coincidence that our universe is so perfectly tuned for us? There's no coincidence. It's a selection effect. We call this the anthropic principle. We could only exist to ask the question in a universe that allows us to exist. A fish doesn't marvel at the miraculous properties of water, it just finds itself in water. To many scientists, this feels like giving up, a retreat from finding mechanical explanations. But it has theoretical backing from string theory, which predicts a landscape of 10 to the power of 500 possible universes with different laws. And it has a track record. It made a successful prediction about the value of dark energy, arguing it should be small but non-zero, which is exactly what we found. Maybe it's not a cop-out. Maybe it's the final, humbling truth. We're not the center of the universe. Our laws of physics might not even be the only ones. We are just one lucky ticket in an incomprehensibly vast cosmic lottery. So, after auditing the evidence, where do we stand? That tiny magnet on your refrigerator has led us to the absolute edge of human knowledge. It reveals a crack in reality, a fine-tuning so profound it looks like the universe is rigged. We are now faced with three radically different potential realities. 1. Where reality has more dimensions than we can see, and gravity's power is spread thin across a vaster cosmos. 2. Where a hidden world of shadow particles engages in a perfect, silent dance of cancellation to protect our stable existence. Or 3. Where our entire universe is just one winning lottery ticket in a multiverse so vast that even impossible coincidences are inevitable somewhere. Each explanation is more mind-bending than the last. Each requires us to abandon a cherished assumption about how the world works. And right now, the data is silent. The LHC has found no new particles. The tabletop experiments have found no new dimensions. The universe is guarding its secret. The pencil remains balanced, and we have no definitive reason why. But this isn't a story of failure. It's a story of a frontier. The hierarchy problem is the giant X on our map of reality that says here be dragons. It is forcing us to question everything, including our own aesthetic preference for what a natural or beautiful theory should look like. And one thing is now crystal clear: the world you feel, the solidness of the ground, the simple act of falling, this is a comfortable, low-energy illusion. It's a stable story being told by much deeper, wilder, and stranger rules playing out on energy scales we can barely comprehend. Scale isn't just a background number. It's an active player in the cosmic game. And perhaps the most profound realization of all is that feeling you get when you confront these ideas, isn't just a fleeting emotion. It's an instrument of perception. It's the tool our minds use to recalibrate our understanding when faced with a truth larger than we are used to. Use it. Tonight, when you feel the pull of the earth as you walk, or see that magnet holding up a drawing on your fridge, take a moment. Realize you are standing on the edge of the deepest question in physics. And then zoom out in your own life. Ask yourself, what problem, what worry, what truth feels impossibly large right now? And what happens if you realize you might just be looking at it from the wrong scale? Now I have to know. Which theory blew your mind the most? The idea of gravity leaking into extra dimensions, the hidden world of superpartners, or the possibility that we're just one lucky ticket in a multiverse? Let me know in the comments below. I read every single one. If you believe that asking these questions is what we're here to do, and you want to keep auditing the fundamental rules of reality with us, make sure you subscribe and turn on notifications. You won't want to miss what we investigate next. And for another audit that will completely rewire how you see the universe, click the video on your screen right now.